So, well, first of all, thank you all for the invitation. I feel quite honored to be kicking things off this hopefully less eventful year, although already quite convoluted. So today I wanted to talk about an alternative proof for the integrability of Lie-2 algebras, one based on the Van Est strategy. So let me start there. Associated with any Lie algebra, there is a canonical extension of the image of the adjoint representation by the center of the Lie algebra. And such extensions are known to be classified by the second Chevalley-Eilenberg cohomology, as there is a unique class that encodes this extension. Now remember this theorem of Van Est that tells you that if you have a sufficiently connected Lie group, then the map that differentiates group, smooth group cochains into Chevalley-Eilenberg cochains is an isomorphism or induces isomorphisms in below the degree of connectedness, say. And since, of course, the image of the adjoint representation is a linear Lie algebra, one can use exponentials to construct an integration, and one can always pick such integration to be too connected. And therefore, the Van Est theorem tells you there exists a unique class in the group cohomology that goes to the classifying class of the canonical adjoint extension via the Van Est map. Now, the second cohomology of groups also classify extensions, and therefore one's got an extension of Lie group by the center, and such extension goes over to the Lie algebra you started with when you differentiate. And so this fairly simple strategy of integration that was devised by Van Est and published in the early 1950s, it rests upon the development of both Lie group and Lie algebra cohomologies, as well as a Van Est map and theorem, so the relationship between them, and a couple of other necessary ingredients that I list here. Indeed, notice that attempting to use this strategy to integrate, for instance, Lie algebroids would take us so far because, of course, there are groupoid and algebroid cohomology theories that have the prescription that they classify extensions, and there is a Van Est map and a Van Est theorem, but certainly there is no canonical adjoint, say, honest adjoint representation, and therefore there is no exact sequence to start with. And if one would use this strategy, the best theorem that one could get is this theorem of Marius Kreinig, where you see that the existence of the extension as well as the existence of the two connected integration are asked on the onset as hypotheses. Now, I'd like to apply this strategy to integrate Lie-2 algebras. So let me tell you a bit of what is known and what isn't.
Camilo?
Compatible differential on its exterior differential algebra.
Camilo?
Sorry, on its exterior algebra.
So
yeah.
we lost you for like 10 seconds. So maybe it would be good to repeat the end of the last slide.
So I was saying that recall that a Lie algebra structure on a vector space can be equivalently defined as a differential on the exterior algebra. And this correspondence can be actually extended, upgraded to an equivalence of categories, where Lie algebra homomorphisms go over to maps of complexes. And this I will use to define fairly economically what an L-infinity algebra is. So an L-infinity algebra structure on a graded vector space is simply a differential on its graded algebra, sorry, on its exterior algebra. But now, since there is a grading, you need to take care of that grading well, you need to take care of that grading. This definition I am using because of what follows, as opposed of the usual definition in terms of n-ary operations that satisfy Jacobi type relations, but this other definition also comes into play because Lie-2 algebras are going to be defined for me, strictly Lie-2 algebras, as L-infinity algebras that are concentrated in degrees -1 and 0, and whose ternary bracket vanishes. The good thing about this prescription is that one can also write representations on graded vector spaces simply as differentials on the symmetric algebra, graded tensoring it with the graded vector space. And this is, well, this makes it easy to, well, get the fact that you have an obvious cohomology theory, and also as it so happens to be, these objects in general admit adjoint representations by essentially adding all of the n-ary brackets. Now these are say 1.5 of the ingredients that we needed to run Van Est strategy. And before moving on, let me tell you why, and let me tell you why I call this the Chevalley-Eilenberg complex. This complex has been shown to extend the Lie algebra, say the Chevalley-Eilenberg complex of a Lie algebra and its adjoint representation, in that, for instance, one parameter infinitesimal deformations of a Lie-2 algebra coincide with 2 cocycles with values in the adjoint representation, but also, and more relevant to us, the second cohomology of these Lie-2 algebras classified with values in a 2-vector space, in a graded vector space concentrated in -1 and 0. They classify appropriate types of extensions. This is already good enough, but indeed not suitable to run Van Est strategy, and I'll tell you why. If you have that this is my notation for a Lie-2 algebra and this is my notation for a 2-vector space, then this is how the complex looks like. And although it's fairly intimidating, let me point out that it is cut out of usual Chevalley-Eilenberg complexes with values in symmetric powers of G. That is the one sitting in degree -1. And of course, if you would use the Van Est map as you usually do, well, there is no way where there is no place where the symmetric powers are going to appear, and therefore, well, there is no hope in attempting to generalize this well, straightforward.
Hi, Camilo. May I ask a short question? Is it the complex? I'm not so sure. Is it the complex of the Lie algebra together with its representation of the homotopy?
Well, in general, yes, it is. But well, later on, I will take them to be strict representations.
Over here is not yet strict, so you will have cross terms like a where is the cross term? Wedge.
Right.
I didn't.
Those are not appearing. They would appear here. If you go here, you would have H star and then wedge 2 of H with values in this. You see, each of these rows is the Chevalley-Eilenberg complex of H with values in this vector space. So the mixed terms would start appearing here. and the fact that the representation is not yet and a strict representation appears actually in these diagonals, in these maps. Oh, I just wrote one, but yeah, the going down of the maps in this differential is represented by the up to homotopy in the representation. And this one is L3, for instance, and I will deal with strictly two algebras. So this map will not appear when...
Okay, yeah, right. Going down is the homotopies, right. Right, you're right. Thank you very much.
It's okay. So I wanted to, well, make the point that since the binary bracket in an L-infinity algebra is of degree 0, then and G sits in degree -1, then it seems as though G has no Lie algebra structure. And in fact, if you look at this complex, the Lie algebra structure of G is notoriously missing. But one can actually endow G with 1 and get what is known as a cross module. So a cross module of Lie algebras is simply a Lie algebra homomorphism together with an action by derivation that satisfies these two things. And if you start out with an L-infinity algebra in general, you can write a bracket for G, and in the case of a strictly two algebra, then L3 is 0, and this thing is actually a Lie algebra structure on G. The way around the fact that these two, say, inconveniences of this complex, that namely that on the one hand, the Lie algebra structure of G is nowhere to be found, and that there appear symmetric powers of G. Well, one way around it is to consider the Lie two algebra to be a groupoid. And this comes about by extending the usual Dodkan correspondence to prove that the category of cross modules of Lie algebras is actually equivalent to the category of groupoids internal to groupoids objects internal to the category of Lie algebras. And let me tell you how this correspondence work. If you start out with a cross module, then you build a groupoid whose space of arrows is the semi-direct sum of G and H with respect to the action that you have by definition, and then the rest of the groupoid structure is simply given by the usual Dodkan correspondence. And you see, because of the way the multiplication is defined, well, you see that you actually get a groupoid because you can write explicit inverses. And conversely, if you have if you start out with a groupoid internal to the category of Lie algebras, that is a groupoid where the space of arrows and the space of objects are Lie algebras and all structural morphisms are Lie algebra homomorphisms, then you can restrict the target to the kernel. This gives you a homomorphism of Lie algebras, and using say the adjoint adjointion by units. So the bracket in the space of arrows, you can write an action by derivations that turns out to be to define a cross module. So now let me present some direct evidence that maybe the groupoid nature of a Lie two algebra might be of use. I will deviate from the standard notation, and I will use subscripts to represent spaces of P composable arrows. And with this, one can consider the nerve of the Lie two algebra presented as a Lie groupoid. And using the equivalence that I presented before, you can dualize to get this co-simplicial object in the category of complexes. And using the usual combinatorics that one performs to get the groupoid co-chain differential, you get a double complex where columns are Chevalley-Eilenberg differentials and rows are groupoid differentials. So these rows are subcomplexes of the groupoid co-chain complex of powers of the Lie algebra you started with. And if you would take a look at the second cohomology, so you take a 2 co-cycle, that is a pair where omega being a 2 co-chain has Chevalley-Eilenberg differential equals to 0, and then these are the two relations. But the fact that this omega has is a 2 co-cycle in the Chevalley-Eilenberg complex of H tells me that there is an extension, and actually the other two relations simply tell me that they tell me that well, I can extend a cross module structure and actually build an extension of cross modules that, since this category is equivalent to the category of Lie groupoids of groupoid objects in the category of Lie algebras, well, this is an extension of Lie to algebras anyway. and this tells you what you can further prove is that if you have cohomologous 2 co-cycles, then they produce isomorphic extensions. My contingency is that one should regard the double complex associated to a Lie to algebra presented as a Lie groupoid as the Doltkan counterpart to the Chevalley-Eilenberg of complex of the Lie to algebra. And in fact, if you tensor the double complex with a vector space, the second cohomology actually classifies extensions by the unit vector, by the unit groupoid of the vector space. And maybe just full disclosure, what's the deal with this additional hypothesis? This is just telling you that the representation is not simply a representation of H, but that is compatible with the rest of the Lie to algebra structure. and this, well, is a strict representation. So let me halt here and tell you a bit about the global side of this story. Having so many equivalent categories to describe Lie to algebras, it is rather easy to define Lie to groups, or rather strict Lie to groups. So one can equivalently define a Lie to group to be a groupoid object in the category of Lie groups, or as a cross module of Lie groups. That again, by definition, is a group homomorphism together with an action by automorphisms that I'm writing here as an exponent, and that satisfy these relations. And do notice that this is what I will mean by integrating, that in either presentation, it is fairly clear that if you go and apply the Lie functor to everything, you're gonna get, well, a Lie to algebra in either presentation. Now, once again, this equivalence is given morally by a Doltkan type correspondence, where if you start out with a cross module, you build a groupoid where the space of arrows is the semi-direct product with respect to the action that you have by definition. And then the Doltkan correspondence gives you the structural maps. And once again, because of the way of that the multiplication is defined, well, these objects are actually groupoids. And conversely, if you start out with a Lie groupoid internal to the category of Lie groups, you use the same prescription and use conjugation by units to define the action by automorphisms. Here, this vertical bow tie is going to represent here and later on the multiplication inside the group of arrows. Now, it isn't in the cross module presentation that Lie-2 groups, strict Lie-2 groups, were widely studied at the beginning of the 1940s when Whitehead used them to classify homotopy 2 types. But later on, in the late 1980s, they were well, the groupoid side of things was exploited by Lodi, I don't know how to pronunciate his name, where he argued for the classification of homotopy n types by what he called n-cat groups, or groupoids, which are essentially what we now call n groupoids internal to the category of groups. But this classification, I mean, when they were studied like that, they were, I mean, there was no topology or smooth structure to be found. What is true is that there were a whole bunch of cohomology theories that were developed, adapted to certain type of representations that were useful at the time, and those were cut out of this double complex that has columns, usual group cochain complexes, and rows, groupoid cochain complexes of powers of the Lie-2 group you started with. And the upshot of this object is that, well, in fact, the total cohomology of this double complex classifies extensions by the unit groupoid of the vector space. And note that this is especially useful for us because one's got a natural candidate for a Van Est map, namely, since columns are group cochains, I can use like the classic Van Est map to go over to the columns of the double complex of a Lie-2 algebra, which are usual Chevalley-Eilenberg complexes. And in fact, when you assemble them together, they are compatible with the horizontal maps. And furthermore, if you restrict to the second cohomology or to 2 cocycles, then this map coincides with differentiation or linearization of extensions. This is what I tried to summarize by this diagram. Now I will show you a Van Est type theorem adapted to this situation, but in order to do so, I will need to make a brief detour and show you a neat way of rewriting the Van Est theorem using the mapping cone. So when you have a map of complexes, the mapping cone is defined by this. And it's got the neat property that the cohomology of the mapping cone is 0 whenever there are induced isomorphisms in cohomology. You see, this is exactly the conclusion of the Van Est map. And the proof of this is fairly simple, so let me show you how to do it. You first point out that the mapping cone fits in this obvious exact sequence, and then the induced long exact sequence in cohomology has as connecting homomorphism the induced map in cohomology. So the rest is straightforward. This can be extended to maps of double complexes in the sense that here the mapping cone, I said that is a complex. It is so if and only if this map is a map of complexes. In the case of maps of double complexes, what you can do is, well, restrict to each column that is going to give you a map of complexes, then take the mapping cone that gives you complexes, and you can just use the horizontal differentials, and this is going to build a two-dimensional grid that is going to be a double complex if and only if the map you started with is a map of double complexes. And with this, one can prove a Van Est type theorem simply by saying, okay, I've got these maps that I told you are assembled column-wise with usual Van Est maps. So I have this double complex that has columns, the mapping cones, and the horizontal are simply the induced maps. And now I can filtrate this double complex by columns, and I get a spectral sequence whose first page looks like this. And you see the fact that H is K connected is going to make this first column vanish below K. And then using the Kunet formula, one can see that this actually vanishes below the diagonal. So the spectral sequence converges to 0, and one proves that the cohomology of the map is 0, which is to say it induces isomorphisms in cohomology below the appropriate degrees. What's left is, okay, we now have cohomology theories that classify extensions. We have a Van Est map.
Camilo, what does this say? That like this total phi equal to 0. What does it mean? What does it mean?
Well, it means here, as I told you, if you have a map of double complexes, this is a map of double complexes, then produce that is a map of double complexes if and only if this thing here is a double complex. And now I can take the total cohomology of this object. That is
right. For example, the cohomology of mapping cone equal to 0 before it means something, right? It probably means
right.
A and B, they are, yeah.
It means this. It means that then the induced mapping cohomology between the total complexes here, between the total complex of A and the total complex of B, are isomorphic. This is what this theorem is saying.
Right. So this for complex and double complex is the same, and here, what does it mean? Like phi, well, should I interpret phi as something between what and what?
Well, phi is the map that I defined before. It's this map that goes from the double complex of the Lie group, which is this, to the double complex of the Lie algebra, of the Lie 2 algebra, which is
okay. So that is the Van Est. Okay, using this way you show it's the isomorphism. Okay, I understand. Okay,
right.
Thank you.
My pleasure. So yeah, so this Van Est theorem is saying, as I told you, simply that if you have well, that there are induced isomorphisms in cohomology between the cohomologies of these double complexes naturally associated to the Lie 2 group and to the Lie 2 algebra, if you have this connectedness hypothesis. And well, once again, what is left? So we had already a cohomology theories that classified Van Est theorem. We have an adjoint representation, which was naturally associated to any Lie 2 algebra. So what it's left is that we need integrations. So if you write this, if you use this notation for the category of linear self-functors, then as a fact, you can use the exponential as well to integrate, of course, an adapted exponential to this categorified version of the story to integrate linearly to algebras, that is linear subgroupoids of GL phi. And that means that we have all the ingredients to run Van Est strategy, and this is the theorem that comes out of it. where, of course, what I'm hiding, or what this hypothesis is hiding, is that well, we want the kernel of the adjoint representation to be an honest vector space, because I haven't told you anything of what happens when you take values on groupoids, on two vector spaces more general than unit vector spaces, than unit groupoids. And well, you may ask, why are you so hopeful that you're going to find an integration? And the answer is because it was already proved by Yunghai Zhang and Cheng-Chang Zhu that in fact strictly two algebras are integrable, and they do so going well, using the Lie algebra path strategy. So they actually integrate the action. So they look at the Lie 2 algebra as being presented by the cross module. Of course, the Lie algebra homomorphism you can integrate, and then they integrate the action. This is the theorem, and this action, well, satisfies what needs to satisfy. But maybe at this point, no, well, yeah, maybe at this point I will say that because of the nature of this proof, this is a proof for the integrability of finite dimensional Lie 2 algebras. And although in infinite dimensions, you might not have pieces of the Van Est ingredients, it actually runs in infinite dimensions. And it was actually used by Van Est and Cohomological to come up with the first example ever. So historically, the first example of an infinite dimensional Lie algebra that is not integrable. So, well, what I will do now is to extend these double complexes to well, the case where representations take more general values. In order to do so, I need to tell you what representations are. I will not bother you with the details of what they are, but I will well, stress that on the one hand, these are strict morphisms. So there is no, for the experts, there is no row 2 going from the wedge of this over to the other side. And what it consists of is of 3 maps. Namely, a map that allows you to take sections of the structural morphism of the 2 vector space, and 2 representations that appropriately commute. And this is also the case in the Lie 2 group for the case of Lie 2 groups. So representations also consist of a map that allows you to take sections and of a couple of compatible representations. And well, these objects are subject to relations that encode the fact that these are not simply maps of complexes, but rather cross modules. So there is a lot of equations that I'm hiding. Let me just tell you a bit about this, because I haven't told you anything. So there is a natural space that serves as the generalization of the general linear group. Namely, this is a category where the space of objects are automorphisms of the Lie 2 group. That is, functors that also respect the group structure. And then the space of arrows are natural transformations between these functors, but natural transformations that are special in that they are group homomorphisms. Okay, so now I'm ready to tell you what happens when taking more general coefficients. So when taking more general coefficients, you have a 3-dimensional grid that is constructed on top of the 3-dimensional lattice that I'm writing here explicitly. Notice that I replace now the symmetric powers of G with antisymmetric powers of G. And now the front page of this triple complex, of this three-dimensional grid, it is the usual one, the one that we had already seen. So you have columns that are Chevalley-Eilenberg complexes with respect to one of the representations that you have for free because you are working with a representation. And then as you move along the P direction, so in the groupoid direction, you pull back this representation by final target map, as you do with Lie groupoids. And then all the horizontal maps in this drawing, all the horizontal complexes in this drawing are Chevalley-Eilenberg complexes of G, which again, that was the point that I made at the beginning, that the Lie algebra structure of G was conspicuously missing. Well, now it appears, it shows up and a lot. And the only thing that I need to fix is that, well, this complex doesn't start where it is supposed to start, but I do have this map as part of the data of the representation that allows me to go to take sections, say. And in general, at any point, I'm going to use this other representation pull back along the Lie algebra homomorphism, that is the structural morphism of the cross module, reinterpreted to take values here after evaluating elements, say Q elements of GP. The successive columns are, again, Chevalley-Eilenberg complexes. This time round, they are Chevalley-Eilenberg complexes with respect to this representation that I believe is called the dual representation. And well, as you go farther back in the R direction, well, you get this formula for the representation, which is actually a formula defined for representations taking values on all R multilinear maps from G with values in W, and which are actually the same representations that appeared in the Chevalley-Eilenberg complex. For the case of Lie2 algebra, of Lie2 groups, then again we have a three-dimensional grid that is drawn on this three-dimensional lattice, where I'm writing C to mean functions from the group into this vector space. You can think of them also as sections of the trivial vector bundle. Once again, the front page is the same that we already saw as the double complex. It is not a double complex. It looks like the double complex that we already presented. So the group cochain complex of H with values in representation. And as you move along the P direction, you just pull back this representation by the final target map. And again, this time G appears explicitly using the pullback of the second representation that we had along the structural morphism of the Lie2 group. But this time around, when you go up, the representation changes, and now certain groupoid cochain complexes start appearing, namely in the horizontal direction, there appeared Lie group bundle cochain complexes, and with fiber G, of course. And in the vertical direction, there appear the groupoid cochain complexes of the action groupoid of H that by definition acts on G. And when you go farther down the R direction, then you just consider the diagonal action. This is in general what happens. The P direction, the Q direction, and the R direction and are built out of groupoid cochains, which will be especially useful for us because there is a Van Est theory for groupoid cochains. And I decided to present this just to say that, well, these representations might seem arbitrary, but they are not. In fact, when you have a representation of a Lie2 group on a two-vector space, there is a natural notion of a semi-direct product of them. And this semi-direct product you can regard as a VB groupoid. So a vector space, a vector bundle over your groupoid that is also a groupoid. And these were proved to be equivalent to two-term representations up to homotopy by Alfonso Gracia-Saz and Rajan Mehta. And well, these representations that are showing up here are not really arbitrary, but rather they have to do with the data defining that representation up to homotopy. Now, I've tried to restrain from calling these three-dimensional grids triple complexes because they are not. The thing is, now the front page that I showed you before that commuted no longer commutes. In fact, when you go around a given square and you evaluate.
So may I just surely are the VB group over here? Is it like the one of the group point is GH going to G, that one?
Right.
Oh, the other is it just times W and V in a way.
Right. You're absolutely right. So I mean, the way you can think about it is, as I just told you, say you have a Lie2 group and you have a two-vector space and a representation. Then you can build the semi-direct product of them, right? So once you have the semi-direct product as a product, the thing is the space of arrows times a vector space. That is going to be a vector bundle over your space of arrows.
Right. So it's somehow a trivial vector bundle where you just.
It is a trivial vector bundle, indeed.
Yes.
But it is not trivial as a groupoid. So there is information there that is not missed by the representation up to homotopy. Yes. Okay. So as I was telling you, these are not triple complexes because although in this drawing, horizontal edges are in fact double complexes. So those differentials commute, and also the ones parallel to the screen are double complexes. The ones that are supposed to be read off as perpendicular to the screen are not. The first one that we had was the one that I presented before, the one that in the case when W was equal to 0 was an actual double complex. It is no longer a double complex. It does not commute, but it does so up to isomorphism. Namely, if you go around the two ways you can go in a given square, and you evaluate, you get elements in B, and B is a two-vector space, so there is a notion of isomorphism of elements. And if you go farther up R, then what will happen is that these two maps are not equal, but rather homotopic as maps of complexes. And this happens for both Lie2 groups and Lie2 algebras. And the miraculous thing is that you can actually write explicit formulas for the isomorphisms and for the homotopies, and you can add them up to all of the other differentials, so that when this is not giving me 0, I add the isomorphism, and now they are 0. Unfortunately, when doing so, one introduces a bunch of other relations that will fail to vanish. So one needs to, well, look at them, and then you realize that once again, though they don't vanish, they do so up to isomorphism in the front page or up to homotopy in the other pages. And you can again write explicit formulas and add them up, And in the end, there is a point where simply you have nowhere else to go. So you have all of the homotopies. That is what I'm writing here. I call these homotopies difference maps because they measure the difference between going one way around the square or the other. And well, they have this grading. I wanted to show you how they would look like. So here I'm writing, well, these first three differentials are the differentials in the three-dimensional lattice, in the three-dimensional grid. And these delta K are the difference maps or the homotopies. And I wanted to show you at least an example of how they look like. So here's how they look like for K equals 1. It is something that resembles the determinant by minors formula, right? Because you have here, well, you see Q elements that live in GP. And then what you do is you remove the first line here, and then you go removing column by column, and you use the omega that you have to multiply it. Now, in the case of Lie2 groups, you can also, and the good remark about this complex is that in the lowest degrees, it is isomorphic to the Chevalley-Eilenberg complex, which is good because, well, this means that this complex classifies extensions, abelian extensions, as the Chevalley-Eilenberg complex does. And also, if you want to, well, push a bit ahead, indeed, they also help you classify one-parameter infinitesimal deformations and so on. So this is to add to my point that this should be regarded as the Doltkan counterpart of the Chevalley-Eilenberg complex. But the full disclosure, I have certainly not been able to prove that these complexes are isomorphic or weakly isomorphic or anything. I know that for the first degrees, they are equal. Then at some point they start deviating from one another, but they are still isomorphic in cohomology. And then at some point I am able to define a map from this complex to the Chevalley-Eilenberg complex that respects co-cycles, but I have not been able to find a way back or a homotopy or nothing like that. Okay, now in the case of Lie2 groups, you also have such feature that you can, well, add all of the homotopies that I call difference maps, and you have indeed a complex. This complex has the property that its second cohomology classifies abelian extensions. In this notation, the three differentials of the three-dimensional grid are written here. And I wanted to show you how the formulas for these difference maps look like, and this is it. And of course, this is just to tell you, well, I don't really know what's going on. That I can write the formulas, but I don't know why they are like so. I have been able to write several classes of formulas and prove the relations they satisfy between them, but that is really painful because I have still not been able to define them in general. I can tell you, maybe making it smaller, I can tell you a bit of what's going on and what I think the gist of this is. So what I think this is related to is to the actual like double group weight structure, because you see these elements start taking values in sort of so let me just show you here. So this is a general element in G P plus 2, Q plus 2. That means P composable arrows and Q of them. So here I write this bow tie to represent that I'm joining two of them. This is the groupoid structure. And vertically, I write the vertical bow tie to mean the group structure, the other algebraic structure. And you see what happens is at the very beginning, all of the elements here are taking values are doing this, which is delete the square here, which has to do with the fact that here I have a 2 and a 2. So this is the square that I'm deleting. And now what's going to happen is that there are going to appear several ways of multiplying these between them with respect to these two structures. So for instance, here I have the full square multiplied, and here I have just a bit that is joining like so. And then here I have a bit that is joining like so. And then here, these elements that are triple, well, they represent sort of doing an L. Of course, this is nothing like this that I'm telling you. I'm embarrassing myself because I'm just confessing how little I understand this. I wanted to show you what the formulas look like anyway, and tell you that although they are so complicated, up to degree 5, for sure, this builds a complex. So I'm now going to conclude by telling you that there is a Van Est map. You can define a Van Est map between these triple complexes, that you can do so at the level of the three-dimensional lattice. And you see this vector R that I'm writing here, these are like usual Van Est maps. So in the Van Est map, you start differentiating along different directions, and then you antisymmetrize everything so that you get something that is antisymmetric. Here, you do this twice, and this turns out to be no accident, really. What you can prove is that this map phi is a composition of two Van Est maps. And to explain a bit about how this comes about, let me tell you. So when you have a constant P, I told you, you have an actual double complex. And that double complex turns out to be an analog of the double complex that we had for Lie2 groups, but in the realm of double groupoids. So this object here, that is this object here that is a double groupoid that in this direction is an action groupoid and in this direction is a bundle of Lie groups. Well, it's got an naturally associated double complex, which comes from putting, well, this is a groupoid, so go ahead and take the complex. This is a groupoid, so go ahead and take the complex. And then every single element on the nerve is going to be a groupoid, so you can take the complex and do the same horizontally. And since this is a double groupoid, I can look at the first infinitesimal version of it, namely its LA groupoid. And now this object is a Lie algebroid, and this is a Lie algebroid, and this is an object internal to the category of Lie algebroids. And you see that equivalence that I told you at the beginning, that Lie algebras structures on a vector space coincide with differentials on its exterior algebra, actually extends to the category of Lie algebroids. So a Lie algebroid structure on a given vector bundle is equivalent to having a differential on its algebra of exterior sections. It's on its exterior algebra. And so that equivalence of categories that was proven by I don't remember, sorry. By whom? Well, sorry, I forgot. This equivalence of categories allows me to write Weintraub thank you, allows me to use the same trick. So now I have a Lie algebroid that I can consider as an exterior differential on the exterior algebra, and then all of these maps are going to be maps of complexes that I can well, sum permutating, that I can sum after that I can take like cyclic sums of to produce a double complex, out of which I can go again and differentiate and prove that in fact the map that I wrote is a composition of going from the double complex, this is in a single constant P page, of the double complex of a Lie groupoid, of the double Lie groupoid, to the double complex of its LA groupoid, to the double complex of its double Lie algebra. And of course, since we do have a Van Est map, a Van Est theorem for Lie groupoids, then I can use the same trick that I did before when I proved the Van Est type theorem that I presented before, to prove this more general Van Est theorem for general coefficients. And since we now have cohomology theories that classify extensions, a Van Est map, a Van Est theorem, and a joint representation, and
Camilo. Hey, Camilo, I think we lost you when in your punchline, so you should give us the punchline again, I think.
So my punchline, what was my punch?
Right, I think you're frozen again. Is it just me, or it's happening to everyone else?
Yeah, it's happening.
Everybody's problem.
Hey, Camilo, so yeah, we keep like losing your audio for like so okay, one last time. Let's try to do this, the end of this slide again.
Sorry, was this like
Sorry.
so the whole lecture?
No, it was really
No,
at
no,
the
no,
end,
no.
literally at the very end.
Okay. So I was just saying that since we now have all the ingredients, namely a cohomology theory for Lie groups, for Lie two groups, and a cohomology theory for Lie two algebras that suitably classify extensions, we have a Van Est map, this Van Est theorem that is for general coefficients, and a joint representation, and the integrability of Lie two algebras, then we have all the ingredients we need to run the Van Est strategy, and therefore proving the integrability of Lie two algebras anew. And that was all I wanted to say.